In this lecture, let us start discussing about the panel method. We have discussed about potential flow at length, where we said that in the incompressible flow domain, the governing partial differential equation is Laplace equation, and if you go to the compressible domain, then you have the velocity potential equation. We can also show that Laplace equation can be derived from the velocity potential equation under the incompressible limit. So, we again recall that this caters to irrotational flow, and we have learned about different solutions of Laplace equation, which we have named as elementary flows. For example, we have learnt about uniform flow, we have learnt about source, sink, we have learnt about doublet, we have learnt about point vortex, and also we remember that because Laplace equation is a linear partial differential equation, if you combine these elementary flows in certain linear combination, that also is a solution of Laplace equation. So, keeping that in mind, we have also discussed about some benchmark kind of flows. For example, non-lifting or lifting flow past a circular cylinder, a semi-infinite body, the Rankine half body, etc. So, now the problem that we have in hand is that whether we can solve potential flow past an arbitrary shaped airfoil. So, we do not have much control over the shape of the airfoil. It can have an arbitrary maximum thickness, maximum camber, the angle of attack may also be varying over a wide range, etc. So, especially when we look at large thicknesses, large camber, etc., you know that the thin airfoil theory will become inaccurate, because there are approximations we have made in the thin airfoil theory, which will be violated to a greater extent. But from a practical point of view, we may actually like to solve problems of this kind, because thin airfoil theory would make our life very restricted. In such a situation, what is the way out? The way out is that let us not any longer look at the problem in a simplified manner that thin airfoil theory looked at, that where we had a vortex sheet, a continuous vortex sheet, which was distributed over the chord length of the airfoil, and then we tried to make the airfoil a streamline of the flow. So, there we had an analytical solution which could give us the solution to the flow. But the moment you make the thickness and camber vary quite a bit, there is no closed form solution available anymore. So, we then go for a numerical solution. So, we were discussing earlier that what are the situations where CFD becomes important. So, this is one where you do not have an analytical solution anymore. So, the approach that we will take over here is that we will set out with the problem of solving a lifting flow past an arbitrary airfoil. all right. And therefore, it could be a cambered airfoil, and even if you look at 0° angle of attack flow past an airfoil of that kind, you will have a lifting flow. And of course, at an angle of attack, until unless it is a 0 lift angle of attack, that airfoil will continue to generate lift at other angles also. The same is the case for symmetric airfoils also, if it is not alpha equal to 0°. So, in such a situation, you have a net circulation around the body, and we came to know earlier when we were discussing about elementary flows that only point vortex can help us do that. And then from Kutajoukowski's theorem, of course, you can show that presence of gamma is also ensuring presence of a lift acting on the airfoil. Now, instead of defining a vortex sheet of this kind, in the panel method, we will follow a different procedure, where vortices will be placed on the surface directly, and they will not be placed as a continuous vortex sheet, but rather in a discrete form. So, what is the advantage in doing that? The advantage is that you are not attempting for an analytical solution, you would actually go for an approximate solution, and as you attempt that, you are basically following some of the standard steps of a numerical computation, that you first discretize and then you proceed with the solution. So, the moment you discretize, you are actually aiming at the problem from an approximate point of view. So, we have already crossed two steps, that is, we have done a problem definition, we have set out the objective that we want to solve potential flow past an arbitrary airfoil, and we have also decided which would be the governing equation. It will be basically Laplace equation that we will solve, and we will not solve it directly really by discretizing the equation as it is, but rather we will make use of some of the elementary flows and combine them, so that we can simulate the effect of flow past an airfoil which has an arbitrary shape. And once we cross these two steps, we go into the core part of the CFD activity. So, as we said, the third step was the first step of the CFD activity, that is discretization. So, earlier we saw that there could be different ways you discretize a particular domain, but here we will take a slightly different approach to show how discretization works. So, we take the airfoil geometry and we follow the surface geometry, and we break it down into very small pieces, as though you are approximating the geometry using a large number of line segments. Okay. So, this is basically your discretization. Notice that there is a flow field around the body, we are not bothering to discretize that flow domain. So, the discretization is confined to the body surface. Now, this works for a wider range of techniques which are called as boundary element techniques. Or boundary element method. So, panel method is essentially falling in that category. So, we only try to solve the problem on a particular boundary. We do not care to solve for the flow field in general, but in the process we of course have to cater to certain conditions, so that the solution is reasonable, the solution is accurate. That means, streamlines like this will never come out of a solution like what we are trying to attempt, but we will find out still that what is the pressure which is acting on the surface of the body, what is the tangential velocity component on the surface of the body and so on. Here we are solving potential flow, therefore, the flow will slip on the body surface, there will be tangential velocity component, but there will not be a normal velocity component. Therefore, this body will become a streamline of the flow. If we are able to solve the problem properly, this shape will become a streamline of the flow. There will be no flow separation because it is a potential flow. So, we have to remember that this is how we interpret discretization in a problem like this. What about the fourth step, which is essentially the second step in the CFD exercise? We talk about method of solution of governing equation. So, here of course, governing equation is Laplace equation, and we are not going to solve it with any of those techniques that we discussed earlier, finite difference, finite volume, finite element methods, etc. These are the ones which we will use when we solve for the flow field. But here we are going to take a different technique. We are going to use panels on the body surface, and we are going to solve for the strength of the singularities which we will distribute on the panels. That is how we are going to solve Laplace equation here. And then finally, once we are done with the solution, we should be able to get the numbers which we can plot. So, here we can plot, for example, the Cp versus x by c for the airfoil. You cannot plot anything related to the flow field, please keep in mind. Let us move on to the flow solution process then. So, first thing we will do is we will add some more details in the discrete form of the body. For that, we will just remove some of these details that we had put, because we are not solving for the flow field, therefore, these are not important for us. Let us focus on what we have on the body. Each element that we have on the body is called as a panel. So, each segment is a panel, and you can number the panels in whatever way you want. You can start from 1, for example, over here and move clockwise, and that way let us say this is the nth panel, you move on, and let us say somewhere here you have a jth panel, all right. And you have a total number of panels which you have discretized the body into, and you could also use that as n. So, let us not call this as n, but rather the total number of panels as n. So, this will be the last panel which we look at. So, there could be n number of panels, and then we take a point P in the flow field. Let us say its coordinates is x y. We can comfortably set the origin of the coordinate system here. We will use a x y system, and this is essentially the location of the point P with respect to the midpoint of the jth panel. Each panel at its midpoint has a control point. Each panel midpoint is a control point. So, this is broadly the setup that we need, and then we need to look at the incoming flow. Let us say if I have a u infinity coming in at an angle of alpha, and let us say if you are looking at some intermediate panel here, let us say it is an ith panel. So, you can draw the unit normal vector to that ith panel here at its midpoint, and then you can sketch the local free stream direction let us say this is the local free stream direction, which is essentially going to be parallel to this direction, and we will mark an angle beta I, let us say. We will make use of that angle later on in the formulation. So, with this setup in mind, let us first try to figure out what would you like to distribute over the panels. We are going to distribute vortices on the panels, which qualifies this as a vortex panel method, and let the vortex strengths be gamma j for the jth panel per unit length. So, the strength of the vortices distributed over the panels is defined per unit length. Each panel can be of a different length. There are shorter ones, you can see very short ones here near the nose, comparatively shorter ones near the trailing edge, etc., but bigger ones here, for example. That is why per unit length. So, ultimately starting from gamma 1 to gamma n, you would have to solve the strength of all these vortex along the panels per unit length basis. Normal component of velocity at each panel control point is equal to 0. You have to keep that in mind. Also, Kutta condition has to be satisfied. So, there is a finite angle at the trailing edge in this case. So, let us say gamma trailing edge equal to 0 would mean that the trailing edge essentially becomes a stagnation point. The vortex strength can change from one panel to the other. That is why we have n number of unknowns gamma 1 to gamma n. Let us try to find out what is the velocity potential which is induced at the point P due to the jth panel. All right. So, we remember that this is the jth panel, this is the point P, and we are trying to find out the influence. How do we find that out? Let us write it as delta phi j. That will be minus 1 by 2 pi theta p j gamma j d s j, where we will define theta p j shortly. It is given by tan inverse y minus y j by x minus x j. That is how we will define it. Now, this is the velocity potential which is induced only due to the jth panel at that field point P, but there are so many more panels. Therefore, what would be the total influence? The total influence could be a sum of the effects coming from all those panels. Let us say sum of delta phi j's. So, that is sigma j is equal to 1 to n gamma j by 2 pi integral theta p j d s j. That is how we will be able to evaluate the total effect. Now, if you put that point P, which is basically a field point, in the flow field at the control point of say the ith panel. So, let us say control point of ith panel is xi yi. So, in that case what are we looking at? We are trying to find out that if the point P is put to the control point of the ith panel, then what will be theta I j? It will be tan inverse y I minus y j by x I minus x j, and the total influence due to all the panels at the ith panel control point can be written using an expression like this. Okay. So, this is the total potential at ith panel control point. Total potential in the sense due to the distribution of vorticity over the body. That is the total influence we are talking about. Again remember, there is the effect of the free stream which we have not accounted in the calculations yet. So, put together the normal component which is induced at a particular panel control point plus the normal component which will be introduced through the phi calculations that we have done. That means, the influence of the panels should go to 0. Now, what is V infinity n? V infinity n is nothing but V infinity cos beta I. So, what was cos beta I? We have drawn it earlier. The beta I was indicated here. That was the direction between the free stream and the unit normal vector at the control point of that particular panel. So, we are taking a cos component of that angle, that gives you the normal component of V infinity. And then what is V infinity, what is V n phi, sorry. So, V n phi by definition is gradient of phi x I y I dot n I, that is what the definition is. So, what will that give you? That will give you del n I phi x I y I. It is essentially a directional derivative. So, what do you have finally? You have V infinity cos beta I coming from the free stream minus j is equal to 1 to n gamma j by 2 pi integral dsj equal to 0. This is basically the requirement that you have to satisfy. And remember that all the entries here in this equation apart from the gammas are based on the geometry of the airfoil, because the theta ij's are all dependent on the locations of the control points on the panels, and therefore, it is actually coming from the panel geometry. So, these are all panel geometry dependent, and once you specify the geometry, they will just come out as some numbers. So, what do we finally have? We have that objective of generating a set of algebraic equations. You remember that when we were discussing the different steps in a CFD process, we talked about approximating a partial differential equation into a system of algebraic equations. So, here also we are looking at that. So, when we look at that, let us say the equation that we just wrote in the previous page, let us simplify it slightly and write it in this form: V infinity cos beta I minus j is equal to 1 to n, and we will make a simplification here. We will just represent that integral in the form of j I j. So, that will make our lives slightly easier when we write down the algebraic forms. So, what do the algebraic forms look like now? V infinity cos beta I minus gamma 1 by 2 pi j I 1 plus gamma 2 by 2 pi j I 2. Likewise, it goes on up to gamma n by 2 pi j I n, right. And then remember that we have to do it for all the panels, starting from panel 1 to panel n. So, how will this equation look like when we apply it to panel number 1? Let us try to write it down. It is very simple to deduce from that general form. So, you have to just substitute 1 where I arises. So, remember that the second subscript in the j, that is the integral, stands for the panels which are influencing the control point of the first panel. So, that is what is running from j is equal to 1 to n, and we are just for the sake of completeness, let us also write it down for the nth one. So, it will be j n 1, j n 2, and finally j n n. So, this is basically your system of algebraic equations comprising of how many unknowns? N unknowns. So, you have exactly the same number of equations as the unknowns that you have to solve the problem, and it appears to be a very straightforward exercise, but then you have not implemented Kutta condition yet, and that basically turns out to be a problem, because then you will have an additional equation. So, you will have n plus 1 equations to solve n unknowns. So, it is basically an over determined system. So, what is going to be the Kutta condition here? We said gamma trailing edge is equal to 0. So, what does it basically mean? That if the first and the nth panels are of equal length, then it basically means gamma 1 plus gamma n is equal to 0. Why we said equal length was because these are strengths per unit length, they have to be multiplied with the length of the first panel. Similarly, this has to be multiplied with the length of the nth panel, and then you have to sum it to 0. But here S 1, if it is the length of the panel, is the same as S n, which is the length of the nth panel, and then they go out of the equation altogether. So, what it basically means is gamma 1 is equal to minus gamma n. So, that is how we approximately satisfy this condition. So, what do we have now? We have a situation where the Kutta condition must be satisfied, so that the flow leaves the trailing edge smoothly. In addition, instead of using n number of these previous equations, you arbitrarily drop out one equation and you choose n minus 1 number of them. So, n minus 1 equations from previous slide and the Kutta condition equation, which is basically this equation, ought to be solved in order to solve for the n unknowns, which means gamma 1 to gamma n. So, that is the procedure that we follow in order to solve for it. Once we are done with the solution, let us see what we have. This is your F-oil, these are the panels, each one of them have a gamma associated. So, let us say if this is gamma A, this is gamma B, you have a whole lot of them around the body. And if you remember, when we were discussing about a vortex sheet, if there was a tangential velocity u1 above and u2 below, then the local strength of the vortex sheet would determine the jump in the tangential component of the velocity. Inside the airfoil, the velocity should be 0. The airfoil is a streamline of the flow if you have solved the problem appropriately with the appropriate values of gammas. In that case, there is no flow inside, therefore, the u2 here is essentially 0. So, the gamma gives you u1, which is basically the local tangential velocity. And then how do you compute the pressure? You can go to the non-dimensional pressure straight away, and you can say that this is nothing but 1 minus V by u infinity, you can say tangential component squared, and you might as well say it is gamma by u infinity square, and if this is the ith control point, then this would be gamma I. So, that is how you do it. And then that means based on the gamma strengths that you have, you will be able to compute the pressure and you can plot it. So, there comes the post processing step. And then you have to check, of course, that on the wall, what have you satisfied? You have satisfied that the del phi del n should go to 0, phi being the total potential coming from both the vorticity that you have on the body as well as the free stream. Phi should satisfy this property on the wall. Why? Because you are essentially talking about V dot n equal to 0, V being the complete contribution both from the free stream as well as the singularities on the body. While at infinity, very far from the body, what are you going to satisfy? You are going to satisfy the condition that del phi del x is equal to u infinity, del phi del y should be 0 if it is a flow aligned along the x direction, but here it is coming in at an angle of attack. So, you can replace it with u and v, but maybe you can assign a u infinity and v infinity here. How do you find out the circulation? You just do a sigma of gamma j S j over the n panels, and that of course gives you the circulation per unit span, and from there you can compute the lift per unit span. What if you were looking at a non-lifting flow? Let us say symmetric airfoil, angle of attack 0. Then you can still solve it with the vortex panel technique, but what you will get is a symmetric solution above and below the airfoil. You will see that strengths are going to be kind of mirror images, so that they will essentially lead to a cancellation, and therefore, gamma will be equal to 0. There is another way you can solve this. You can use source and sink. So, on the panels you can use sources or you can use sinks, but if you do that, there is an additional constraint that you have to satisfy, that is the sum total effect of those sources and sinks must go to 0. So, let us say if you call the strengths as lambdas, then j number of those j equal to n number of those sources and sinks should always sum up to 0. That means, the total mass outflux from the sources should be balanced with the total mass influx into the sinks. So, that is an additional constraint that needs to be checked for source panel method. That means, a panel method based on sources, or you can mention it as source sink based panel methods. But this approach, the source sink approach, is applicable only for non-lifting flows. So, it cannot be extended to a lifting situation, because with sources and sinks alone you cannot model circulation. So, that is the limitation. So, let us conclude. In this lecture, we had a brief discussion about potential flow solution for non-lifting and lifting airfoils using the panel method, and we saw that in a very simple framework how we can follow the different steps of a general CFD process to solve for potential flow past an airfoil, which could be both a lifting or a non-lifting one. Thank you.